video, we're going to talk about the stability of benzene. The stability of benzene is basically mainly due to the delocalized pi electrons of benzene. This is a very important topic with respect to the A-level syllabus because many questions have been asked in the past year papers. Delocalized pi electrons of benzene. Okay, this this delocalized electron cloud is basically the reason behind the properties of benzenes which are different from normal alkenes. Okay, a general law is the relation of energy with the stability of a particular compound. So a general law relating the two quantities, stability and energy, is that the lower the energy, the higher the stability of a compound, and vice versa. Meaning, the higher the potential energy of anything, the lower the stability of that compound. Okay, so now the stability of benzene can be assessed by comparing the heat of hydrogenation. Heat of hydrogenation basically would represent the energy of the following compounds with benzene. Of these compounds, the cyclohexene and 1,4-cyclohexadiene, and the third compound is 1,3,5 cyclohexatriene, which is basically the calculate structure of benzene containing the three carbon-carbon double bonds and three carbon-carbon single bonds. The old resonance hybrid of benzene, the old structure of benzene. Okay, now let's get started. The first reaction, the first enthalpy change of hydrogenation, cyclohexene, when reacts with hydrogen gas in presence of platinum catalyst, hydrogenation occurs and cyclohexene gets converted to cyclohexane. Okay, the enthalpy change of this reaction, when calculated, turned out to be minus 119.5 kilojoules per mole. Okay, then the same reaction of the second compound, 1,4-cyclohexadiene, when reacted with hydrogen in presence of platinum catalyst and converted to cyclohexane, the expected enthalpy change that we could expect on the basis of the data of the first reaction, the enthalpy change of the first reaction is just multiply the enthalpy change of the first reaction by 2 to get minus 239. I've multiplied this by 2 because basically the double bonds have doubled. The carbon-carbon double bonds are 2 in the second structure. So 2 carbon-carbon double bond would mean twice as much as the energy would have been released. Okay, so basically twice as much energy would have been released in this reaction. So the expected energy was minus 239 kilojoules per mole. But when the experiment was performed, the energy turned out to be minus 231.5 kilojoules per mole, which is basically has some difference. The difference between the two energy levels is there, but it's not very significant difference. It's a very small difference of approximately maybe minus 239 and minus 231.5. Just calculate the difference, you'll see that it's not a big difference. In the third case, when we reacted benzene ring, benzene, the calculate structure of benzene with hydrogen gas in presence of platinum catalyst and converted into cyclohexane, the expected enthalpy change was minus 358.5 because we multiplied it by 3 due to the three double bonds present in this structure. But the experimental enthalpy that turned out was very astounding. This was very surprising because experimental enthalpy turned out to be very, very low compared to the first enthalpy. It turned out to be minus 208 kilojoules per mole, and the difference in the two energy levels is very big. It's 150.5 kilojoules per mole, and this difference is significant. The difference is significant. Okay, so now the reason why this energy difference came in benzene and did not come in the other two is this: the resonance energy, the stabilization energy. Well, not this actually. The difference in energy is due to the extensive delocalization of pi electron cloud in benzene, because the electron cloud is delocalization, it actually stabilizes benzene. And we know that the general law which we discussed above, that was that the greater the stability, the lower the energy, the lower the potential energy of that compound. So this pi electron cloud, which is actually the delocalized pi electron cloud, it actually stabilizes the benzene ring, and increase in stability actually decreases the potential energy of benzene. Therefore, the enthalpy change of benzene also turned out to be very small, which is 150.5 kilo. Sorry, not yeah. The enthalpy change turned out to be very small, due to which the difference in the two enthalpies is turned out to be significant and large, which is 150.5 kilojoules per mole. This difference in energy, this energy 150.5 kilojoules per mole, is referred to as the resonance energy, or the stabilization energy, or the delocalization energy of benzene, which is due to the delocalized pi electron cloud in benzene. Now let's look at the energy profile representation of these compounds. The energy profile representation with the potential energy on the y-axis and the compounds represented on the x-axis. This is cyclohexene, the first reaction that we had. When cyclohexene is converted into cyclohexane, when this has been converted to cyclohexane, cyclohexane has a lower energy compared to cyclohexene, and the difference in the two energy levels is minus 119.5 kilojoules. Then, when cyclohexadiene got converted into cyclohexane, the difference in energy came out to be minus 231.5 kilojoules. And when benzene got converted into cyclohexane, the expected enthalpy change, benzene, basically the Kekulé structure of benzene, when got converted into cyclohexane, the expected enthalpy was minus 358.5. But in reality, the enthalpy change when benzene gets converted into cyclohexane is very lower compared to minus 358.5. It's just minus 208 kilojoules, and the difference in the two energy levels is 150.5 kilojoules per mole. And this difference in energy level, this is the resonance energy. As you can see that benzene is lower in energy, in the potential energy, compared to the actual structure of benzene. Excuse me. Benzene is lower than the actual, the benzene is lower than the Kekulé structure in terms of the potential energy. Therefore, benzene has a higher stability compared to the cyclohexene, the expected, compared to the benzene ring, which was expected. And this stability is due to the delocalized pi electrons. I'm repeating it again and again. This word delocalized pi electron cloud is responsible for the difference in the properties of benzene. Benzene has lower energy than expected, so it has a higher stability than expected. Okay, so benzene is more stable than it usually is expected. Sorry, than it was expected. Higher stability compared to its stability that was expected. Okay, and this is due to the delocalization of pi electrons. This delocalization of pi electrons is also referred to as the resonance of electrons, which makes benzene, increase in stability makes benzene less reactive than alkenes, and hence benzene does not undergo electrophilic addition reactions easily, which alkenes usually undergo. And therefore, a special type of reaction, a special mechanism occurs in benzene, which is electrophilic substitution, and this reaction occurs only in benzene. Electrophilic substitution reaction occurs only in benzene and does not occur in alkenes or other compounds. So basically, due to the delocalization of pi electrons, benzene does not undergo electrophilic addition reactions, because benzene is very stable, and hence it is less reactive compared to alkenes, and therefore it cannot undergo electrophilic addition reactions. Thank you so much.